Hi, grade 11 to 12. Welcome back once again in these sessions, and we're still continuing with Euclidean Geometry. It's our revision, and I just want in this session to really put much focus on how you can prove that something is a cyclic quadrilateral, right? How you can prove that a quadrilateral is cyclic, and also how you can use the tangent chord proof. Okay, so I know that we focused a bit on this knowledge within our sessions, but I really want to emphasize this through these sessions so that you can have a clear understanding of how this goes about and how you can be asked to prove this thing, right? Okay, so it says how to prove that a quadrilateral is cyclic, right? So there are those questions that you mostly you mostly get in your papers that you require you to prove that maybe a certain quadrilateral is a cyclic quadrilateral, right? So there are three ways in which you can prove that, right? And there are conditions within each of our ways to say if you have something like this, then you can prove this and this, then you can finally deduce that is a cyclic quadrilateral. Okay, so before we go into that, let's first explain what is a concyclic points, right? What do we mean when we say concyclic points? When we say concyclic points, it simply means that the points are concyclic, that is, they lie on the circumference of the circle, right? Meaning that we can deduce that our A, B, C, and D are what? Are concyclic because they lie on the what? On the circumference. Okay, so this also implies, or it means, that A, B, C, D is a what? Is a cyclic quadrilateral. Okay, because it has all its points in the what? In the circumference. Okay, but in an exam they can give you something that is not really concyclic, maybe a quadrilateral having maybe 3 of its points on the circumference, but maybe 1 is not on the circumference, and they would want you to prove that that thing is actually a cyclic quadrilateral. Okay, so there are certain conditions. Someone can argue, but how? We don't have a circle around the quadrilateral. How come can it be a cyclic quadrilateral? So we have certain conditions that we can follow in order to prove. And these are converse theorems, right? They are actually converse theorems that we focus on our sessions, right? 3 of them. So the converse theorem of theorem number 4, it says that if you have angles, right, that are inside that oxbow like tie, or rather that lie on the same segment and that are equal, right? So it means that you actually have a circle around those 4 points of that quadrilateral, meaning it will be what? It will be a cyclic quad. And this is the converse theorem of angles in the same what? In the same segment. If you find that this angle is the same as this one, if you just prove that, right, then you can do this. Oh, actually if it was A, B, C, D, then you can actually prove that actually my A, B, C, D is a what? Is a cyclic quad. Why? Because converse angles in the same segment. We know that is a converse theorem. If angles are in the same segment, we can deduce actually this is a cyclic quad. Okay, so you just need to prove maybe that angle A is equals to B, or someone can actually prove that angle D is equals to angle C. Then you can make that deductions. Okay, that is the first way in which we can do that, and we normally use this mostly if we see that the quadrilateral that we are given is sort of like forming that oxbow, right, tie or something like that. Then if you manage to prove that this angle is the same as this, or someone can prove that this angle is the same as this, you can actually conclude, oh, actually there's a circle around that, meaning that it's concyclic because converse angles in the same segment are what? Are equal. Number 2 in green. So also, if now you don't have that oxbow thing, you have something like this quadrilateral like this. What can you prove to prove that this is a cyclic quad? actually, if you prove that the opposite angles, when you add them, you calculate this angle, you calculate this angle. Someone can calculate this angle if possible, and this angle, right? When you add those two angles, they must give you what? 180 degrees. And what does it imply? It implies that the converse opposite angles of cyclic quad are what? Are supplementary. And this is a converse theorem, right? And we talked about it, but it can be very, very useful for us to prove whether a quadrilateral is cyclic or not, right? So in a case where you have such kind of a quadrilateral, what you have to do is just to prove that opposite angles are equals to 180. So what do? You actually calculate those opposite angles, right? So obviously, if they give you a diagram like this, probably there will be angles that you can calculate. Then when you add opposite angle, if you get 180, you can actually conclude that, oh, our ABCD is actually what? Is actually a cyclic quadrilateral. Why? Because of converse opposite angle of cyclic quad are what? Are supplementary. Okay, so the last but not least condition that you can also check in order to prove whether your given quadrilateral is cyclic or not, it's actually the converse theorem of exterior angle of a cyclic quad is equals to opposite interior angle, right? I think that was theorem number 8, if I'm not mistaken. I think it was theorem number 8. If it's not theorem number 7. Okay, so we did this theorem, and we know that if you can manage to prove that in your given quadrilateral, let's just say A, B, C, D, right? If you can manage to prove that an exterior angle D1 is equal to the opposite interior angle, right? Then you can actually conclude there's actually a circle around those points, making it a what? A cyclic quad. Why? By converse exterior angle of a cyclic quad. Okay, so there are 3 ways in which you can prove a cyclic quad. As we summarize, number 1, if you can manage to prove that angle at the same segment are equal by converse theorem, or rather if you can manage to prove that opposite angle of a cyclic quad, they add up to 180, or rather if you can manage to prove that actually an exterior angle is equals to opposite interior angle, then we can now conclude that what? All these quadrilaterals, they are in a what? They are inside a circle. In other words, they are what? They are cyclic quads. Okay, let's now focus on how to prove that a line is a tangent to a circle. I know that we covered this a bit in one of the session, right? But I really want to emphasize this because these are questions that are guaranteed that you can be sure of that they will come in your exam, right? Okay, so we want to prove that a line is a tangent. Let's say, for instance, you have something like this AB. They want you to prove that line AB is actually a tangent to a circle passing through B, D, and what? And C. How can we prove that? Okay, so if you have something like a triangle there, right? So what you actually prove is the converse theorem 9. Okay, converse theorem 9. In other words, we have to prove that the angle between that line that we want to prove is a tangent and the line that forms that triangle is actually equal to the angle subtended by the 2 other lines of the triangle. And this is converse what? The converse theorem 9, right? Then we can now deduce that actually our AB is a what? Is a tangent. Why? By converse tan chord theorem. And that's actually how you prove, right? So they won't give you outside the triangle. So they can give you something inside the triangle, something like this, right? They can give you something like this. And they can actually draw something like this probably, and let's do something like this. Oh no, here, like that. Maybe they want you to prove that AB is actually a tangent CE, to a circle passing through ACE. In other words, what do you have to prove? You want to prove that AB is a what? Is a tangent. So if you find that that line is actually joining a certain point that forms a triangle, it's simple. What you have to prove that is that this angle is actually equals to this angle. The angle between that line and that line of a circle is equals to the angle subtended by the two other lines of a triangle. Then you'll actually have used what? The converse what? Tan chord theorem to say actually there's a circle in that small triangle, because we get that according to tan chord theorem, the angle between a tangent and a chord is equal to the angle subtended by the two other what? By the two other chords. Okay, grade 11 to 12. That's all for today. I just wanted to emphasize on this. I know that we covered them a bit on some of our session, but it's very important for us to also just quickly remind you and to emphasize this, because these are exam kind of question. Okay, otherwise, upcoming next, it's applying the theorems, and we're going to be calculating angles, applying all theorems in one question, right? And actually showing you this strategic approach on how you can apply those theorems on calculating angles, finding angles, and also proving certain things that they want you to prove. Okay, so otherwise, thank you very much for watching. Thank you for joining. Watch out for the next session. That's all for me, and goodbye.